In this video, I will describe the design of the initial transistor presented in 1947 at Bell Labs. In this, we have a plastic stand to hold everything. This is important because plastic is an insulator and contains the electronic flow where we want it to go. There's also a plastic triangle that has two pieces of gold foil on each side. That plastic triangle and the gold foil is being pushed into a chunk of germanium that has both N-type and P-type dopants. And I will explain what an N-type and P-type dopant are in a moment. The plastic triangle has the gold foil elements which are connected to an emitter and a collector lead. Furthermore, the plastic has a spring that it pushes the plastic with the gold foil into the germanium with the objective of getting the two pieces of gold foil very close to each other without actually touching. In the actual experiment, they got the gold foil within 1/2000th of an inch from each other. In the actual experiment on December 16, 1947, a microphone was connected to an emitter, and then they connected an oscilloscope to the collector lead. So what happened is when they spoke into the microphone, they observed a significant gain in signal on the oscilloscope. The exact quote is, "The voice went over the circuit and a distinct gain in speech level could be heard and seen on the scope." So how did this happen? What's actually physically going on, and how does this contribute to the operation of a computer? The key is in the germanium. I mentioned before this idea of P-type and N-type. Germanium is a group 4 element, just like silicon. It has 4 valence electrons. So when you combine them with dopants from group 3 and group 5, what ends up happening is that you can get electrons and holes to freely move through the circuit. This can only be done with electric devices known as semiconductors. A conductor readily transports electricity. An insulator refuses to allow current to flow. So for example, the plastic. But semiconductors are different. You can dope them to be able to have different types of flow. A semiconductor doesn't conduct electricity as well as a conductor, but it conducts it significantly better than an insulator. So how do we get these negative and positive charge carriers? Well, for one, in the instance when you have an N-type semiconductor, this means you are doping a block of a group 4 element. So in this diagram, it's in silicon, but in the first transistor it was germanium. When you have an N-type dopant, in this case arsenic, the 5th valence electron is loosely bound. We see here that arsenic is a group 5 element and is next to germanium in the periodic table. And group 4 also contains silicon. So what happens is you get a thermal vibration of the lattice, and that will actually set the electron free. We see that the electron will actually move. This leaves a positively charged arsenic ion and a free electron. When you have a P-type semiconductor, in this case we have boron. Boron has 3 valence electrons. It is a group 3 element. So what ends up happening is you produce thermal lattice and it can borrow an electron. So you have these electrons and you have holes. The electrons move like that. So we use these positive and negative charge carriers in the semiconductor. And when you put them together, what ends up happening is it allows engineers to design a device that flows in only one direction. You may have encountered one of these already. It's known as a diode. So what happens is when you put the two pieces together and you hook it up to a battery, if you hook the positive to the P and the negative to the N, it will attract the negative towards the positive battery, and it will attract the positive in the P-type to the negative portion of the battery, so you get a flow. If you switch the battery around, the electrons will try to go towards the positive, and the holes will try to go towards the negative part of the battery, which will stop the flow. Which is why when we use a diode, it only allows flow in one direction. When the positive voltage is attached to the anode, the electrons are free to go towards the positive voltage and the holes flow towards the negative voltage. Likewise, when we flip it, they are not free to flow, so there is no current. So let's compare a diode with an actual transistor. It is helpful to think of the first transistor as two one-way current valves. So let's split it in half. On one side, we hook it up with a positive connected to P and negative connected to N, and we do the opposite on the other side. So here we have the anodes connected and the cathodes are connected to the ground. Not to ground, excuse me. The gold conductor is connected to the foil. It's connected in the opposite way in the other circuit. So we actually have two oppositely directed diodes that are almost touching each other. When we use the spring and we get those gold foils, they come so close to touching. So how do these transistors work? When we push those together, you get current flow, and you don't have current flow on the reverse bias diode. And when you get them together, they're so close, but what ends up happening is some of the dopants move from one transistor to the other. So positive carriers get injected into the reverse bias diode, which then creates current flow in both of them. As a result, you are now getting a significant gain. And if you connect a small battery to one side and a large battery to the other, you can get a significant voltage gain with minimal current gain. So let's compare the actual data. The forward current is very close to the reverse current, and I'm going to show you the actual calculations that they presented in the first transistor in a moment. We see that the reverse voltage is significantly higher than the forward voltage. So here are the actual measurements. The forward current is 0.75 milliamps, and the reverse current is slightly higher, 1.25 milliamps. However, the forward voltage is only 0.2 volts, but the reverse voltage is 25 volts. So when we calculate the power, we see that the power consumed is 1.5 watts in forward, but in reverse, we're actually producing 31.25 watts. And we see that the positive and negative doped semiconductors are complementary, which is where the complementary metal oxide semiconductor from CMOS gets its name. And we see that the group 4 transition metals, silicon and germanium, can gain or lose 4 electrons. And the first transistor used germanium, but modern transistors typically use silicon.